Hi everyone. I'm going to try to see how I get to YouTube channels. Yeah, let's see. Okay, to the comments. I want to see the comments because last time. Okay. Channels. YouTube. Yeah, let's see. Okay. The comments. Okay. I want to see the comments because last time. Okay. Hearing an echo. Oh yes, of course. I have to mute this thing. Okay. All right. Still learning how to do this properly, and got the equipment, and this is going to distract me if I see myself. I don't know how to do that. Okay, well, I'll leave it be. Right, so today I am going to continue on the previous video where we built the PIPS, which is our current just a second. No, sorry, I think okay, something went wrong, but it should be okay. So I built PIPS last time and soldered it together, and I promised another video where I talk about the circuitry and how it works and some of the elements that make it work. So this is what this video is about. So if I turn this thing on, if you press the button, you get a random throw of a die. Now, as I said before, it's not random because anything inherent in the circuit. It's just because the states are going very fast, we can't see them. So when we press the button, which is the random event, it just gives us that a number that happened to be or the state that happens to be the current one when we're pressing the button. We haven't seen a 1 yet, but that's the nature of randomness, isn't it? Seriously? Here we go. That's one. Okay. So I have a specimen here that is already ready for the operation, all hooked up. I soldered the headers on the side so we have access to the to all the pins of it's a breakout, and the extreme pins are power, power, ground, ground, plus 8 pins on each side for that correspond to the pins of the chip. So one thing, a new thing that we have is being able to see the wonderful scope that we have. So this camera is not so good and there's reflections, but let's see how it works out, and then we could improve. But this is what we have at the moment. I'm going to plug in the battery of the device under test. Sometimes you see something called a DUT, D-U-T, that's device under test. Sometimes unit under test, or there was another one. Anyway, this is it. And unfortunately, I did set up something. Let me see. I wanted to have. I'm going to try to fix something here. Oh, I know what happened. Okay. Alright, let me fix something. Okay, this is better. Now you can see. It's just because I put a fresh battery inside of the camera, because it empties very quickly, and so it lost some of my settings. And now with this, so we have that. Here I'm going to, well, scope. Oh, right, okay. Sorry, this will iron out the kinks. Okay. So now we have this view, and oh dear, this view. Okay. All right. So we're sorry about all this. So what we're seeing here is the clock, and I guess we'll start at that. Normally after power you want to verify that you have a clock, and this clock is generated through an internal oscillator that's built into the chip. So that's nice, because we don't have to provide an external source for the chip. And now I'm seeing there's another problem. Sorry, I'm gonna need to do this. Okay, so now it's oriented the way it should be. Yeah, we have a clock source, and that's another indication that something is working. So before I say anything and forget, this is based on a design from an Elector project from about 12 years ago called Dicing with LEDs, and I was working on designing my own circuit and researching and so on, and after a couple of days where I was getting somewhere, I found this, and really it's hard to improve on. And so I contacted people I know at Elector and asked for permission to use it for this project, and they kindly agreed, and I'm grateful to them, and so thank you, Elector. So this is the original article, Dicing with LEDs, the circuit diagram, and a bit about how it works, and that is replicated in the written material for this project. If you go to boldport.com/, /PIPS, you'll get to this infographic where there's these circuits and an assembly diagram, which we went through last time. Put this aside. Right. Before we get to the clock, I'll introduce the component. The component is a CD4060B, which is a 14-bit ripple counter with carry, with a built-in oscillator. So the data sheet for this is kind of old school, and there it is. Zoom in. So, see a CMOS 14-stage ripple carry binary counter, divider, and oscillator. So the idea, these devices can be used for many things, but essentially a counter is often used to divide a clock input. So you have a certain clock, and then as the chip counts, it outputs a divided version that is synchronous to the input clock. This, however, device is for the ripple carry binary counter, which is by definition asynchronous, which means that it doesn't change states according to a common clock that's connected to all the logic elements. So there is a diagram here in the front, a very basic diagram of the chip. This is in the Texas Instruments, the device that comes with the chip, but I found that that there's a better diagram in the Fairchild version of the data sheet, which is often the case, particularly with older devices that have been around for a while. You go fishing for information that is missing from one data sheet in the data sheet of the competitor, because those devices, once they have a designated name, they will be compatible for most part, right? There might be some variations in the specification, but a lot of times they'll be similar, and there'll be slightly more information in one data sheet, and then you'll go there and then you go, aha, this is why it's working or not working. It's because the data sheet that you've been looking at is either old or just didn't have enough information. So this diagram, I was going to draw one, but it was unnecessary. We'll get to the clock bit in a bit, but basically the asynchronous part means that there is a signal coming into the first flip-flop. This is a JK flip-flop that then, according to the clock, according to the signal that is coming to the clock, and you can see here there's an inverter, so it's complementary. You have 0, 1, or 1, 0 always. And that goes on and ripples through, that clock signal ripples through to the end, and that's the carry part, where you can connect it to another counter. So you can see that there is no clock. In a synchronous circuit, you'll see that the flip-flops, each one of them, will have a clock, and there's a clock connected to all of them, and everything happens on that clock edge, either a falling edge or a rising edge. here the clock signal just ripples through and is connected to the data portion of the next memory element in this chain. So what in effect we're getting is that this frequency after that first flip-flop is half, the output here is half of the input clock, and that, so that's and then this is a divide by 2, and this is a divide by 4, and divide by 8, and divide by 16. So you can see here that the first output that we actually get is the divide by 16. So we don't have the divide by 2, 4, and 8. The first 3 bits, they just don't go out to the pins. They happen in the chip, but they don't go out to the pins. So we have 16, 32, 64, and so on. And the 2K, divide by 2K, is also not connected to the to a pin on the chip. And I don't have a good explanation, except which is kind of an unsatisfactory explanation, that the package was limited to 16 pins, particularly 40 years ago when these, or 40, 50, can't remember, those devices came out. The packages were fairly standard, and you had 16 pins, and you didn't have 18 or 20. Maybe there was a 20, but there would have been quite exotic. So they had to omit one of the outputs in order to get the rest of the functionality in. So they decided to omit this this output. Why this one and not another? Well, divide by 1,000 by 1K, 1024 maybe was more useful. Definitely don't want to omit the final division. So, though, if anybody knows, it would be good to hear why that happens. And so it's a 14-bit ripple counter, but you only have access to 14 minus 4, so only 10 bits of that counter. And in our design, we're actually only using 3 bits of that counter. So the clock now. So like I said, this has an internal oscillator, which is, again, I'm going to go with a diagram from the Fairchild version of this chip, and here you can see this is an oscillator, basically inverters in series, and here you have a capacitor, an RC circuit, which according to these values have a certain amount of time where they charge and discharge, and that determines the oscillation. And here you have an input to an AND gate that is connected to this node through a resistor, and to the reset. So if the reset is high, this is low, and if this is low, then this is 0, then it doesn't matter which state this is in, this will be 1. right? So 0, 0, 1, and would be 0, and this would be 1. So therefore it's not oscillating anymore. So if this is 0, 0, and this is 1, right? So and you'll see that the in the circuit diagram here, we have this setup connected to those inputs, pins 9, 10, 11, 9, 10, 11, and a switch and a push button that is connected to ground. So there will be a push button here connected to ground. So that means that now, regardless of the state of reset, if we set this, if we press on this push button where this input is set to 0 and this will always be 1 and it won't oscillate anymore, and that's when we get this that's when the rolling of the states ends, and we get a reading of what the roll is of the die. Now, interestingly, in the original article, the specified push button was these push buttons, when it's configured like that, are called single pull, single throw. And then, in addition to that, they'll say whether they're normally open or normally closed. So this is normally open. It's an open circuit, and when you press it, it's closed. But so what that means is that when you press it, it's closed, therefore it stops the oscillator and we get a reading. When it's normally closed, that means that it's not working when it's in unpressed state, and it rolls when you're pressing it. But these are harder switches to come by, so I decided to do it this way. But if you go to the website of the project, you'll see that I specify a normally closed switch that will that the footprint on the board will accept that particular switch, which is a surface mount switch. So that's about this switch. Now the frequency. So we have here the arrangement. These are 470 kilo ohm in parallel, so which is the equivalent of 235 kilo ohms. And then 220 picofarads and 470 kilo ohm on RS, and RX is 235. So if you go to the data sheet again, where is it? Oh, yeah. It's kind of hard to read, but it's telling us that that T, which is the period, is 2.2 times Rx times Cx. So to get the frequency, it's 1 over T. So in our case, if you look, I go through the calculation on the website, And actually I can show you that. So this is the calculation, 1 over 2, 2.2 times Rx times Cx, and according to the values that we have, we should expect about 8.8 kilohertz of the frequency, right? All right, so 8.8 kilohertz. But when we look at the scope, we see 7.8 kilohertz. It's 1 kilohertz off. And that's actually quite a lot, right? It's more than... it's 1 kilohertz difference, which is more than 10%. And so why could that be? So there are a few reasons for that. One of them is the tolerances of the components that we use. This capacitor is 10% tolerance. So you'll see in the spec they'll say plus minus 10%, sometimes it's 20. This particular one is 10%, and these resistors are 5% tolerance. So there is an element of that. We could, I haven't, but we can go through what are the extremes that we might expect just by virtue of the low tolerance of these components. So that's one element. The other element is that these oscillators, if they are not temperature and voltage compensated, which all indication says that they're not, otherwise they would be here, and it would be celebrated heavily on the sort of highlights of the chip. That means that there will be quite a significant variation between chip to chip, and also because of different manufacturing processes. If it's not, it's not, and it isn't very tightly controlled, and between different conditions on the chip itself. So I looked through the datasheet and I was quite surprised at how relaxed the specification is. So you can see this here. It says variation of frequency unit to unit, so that's across units with this these components, which it's about 45 kilohertz. 45 kilohertz. Interestingly, I also noticed, if you remember here, they say that RS needs to be between 2 RX and 10 RX. And RS here is more than 10 RX. So they kind of violated their own rules here, but I don't think that matters really. So here I had to kind of read this. I'm still thinking I might not understanding this, but it's saying that there will be a variation at 45 kilohertz between unit to unit of 23 kilohertz plus or minus 10%, typical. That's a huge variation. Now here they say variation of frequency with voltage change at the same unit between 5 and 10 volts, you get 1.5 kilohertz. So any small fluctuation is going to give you a noticeable difference in frequency. So in order to see that I'm actually interpreting this correctly, I went to yet another data sheet, the intersil version of this chip, and I'm looking at this here. So operation variation of frequency unit to unit. That's minimum, maximum. Variation from unit to unit, same conditions as before, different voltages at 25 degrees. It's quite high, 18, max 25, 26, 27. And between the same unit, like before, between 1 and 2 kilohertz. So that's a huge variation. The other thing is, you know, here they specify at which frequency, at which temperature, and here normally at the top of the table you'll have the conditions in which this was tested, and so this is at 25, and I couldn't see here in those barely legible graphs whether you know how that will behave across different temperatures, and the other data sheets didn't have that information either. So to summarize, we have a variation in manufacturing, significant variation between unit to unit, and at least across voltage we have quite a bit of variation within the same unit, and that's also true for temperature. I wanted to even try to just touch the chip. Of course it's cool, it's not doing anything heavy. That's not affecting things. It changes a little bit. So this is the explanation why we have 7.8 instead of 8.8. But you know, as long as you know, and you're not expecting that every say product that you're putting it into is going to oops. That every device that you're gonna put it into is gonna have exactly the same frequency. You're fine, right? And for our purposes, of course, it doesn't matter. It could have been higher, it could have been a bit lower. Anything in the kilohertz would have been fine. So yeah, so that's the oscillator part, which is interesting, I suppose. A little adventure into datasheet investigation. I'd like to say that datasheets have improved since, I mean, this says 2003, but this clearly didn't come out 2003. This is 1992. But even modern data sheets always lack what you're looking for. Unfortunately, just the way it is. so you have to experiment, you have to ask around, you have to contact the distributor and ask. Right, so we covered that. Oscillator is working. And now I'm going to connect the other, well, they're already connected, but I'm going to display the other three signals, which is the output of that oscillator. The output of that chip, the counter. Got it, third time. Let's put that here. It's here. Now, one of the reasons why this is dancing around is because it's not the trigger is on channel 1, which is the clock, but the outputs are not necessarily synchronous. Well, they're not synchronous to this this clock, particularly because of all the delay lines of the connections. The connections between the chips, they have to be, well, they're not perfectly matched. So therefore, you're going to have a slight difference in propagation delay, which is the time it takes a signal to go from the output to the input. They're going to be different between the stages, which is partly why you know, the specs are quite relaxed. All right, so I'm going to still getting my way around this scope. Yep, I'm going to trigger on channel 2. Come on. All right. Okay, it's still dancing. Trigger on, I think, three. Okay. Still a little bit of dancing, but it's okay. So now what we're looking at here is the clock signal, the first output stage. Well, the first output that we get out of the clock, first output that we get out of the chip, which is divide by 16, right? And then divide by 32, and divide by 64. And yeah, that looks a bit strange, doesn't it? It's not quite what you'd expect, but I'll explain why that happens in a second, or more realistically, a few minutes. All right, so let's first check the first thing. So I'm triggering now on channel 1. Well, probably best if I trigger on channel 2. Yeah. Right. So here we have the magic happens on the falling edge of the clock. That's why you see the state change here. So remember, we are not seeing the first 3 stages of this ripple counter, so we expect a division by 16. So that's 1, 2, 3, 4, 5, 6, 7, 8. Change of state, and another 8 for a complete period. Right, so this would be the period, and it's just about 16. I'm saying just about because, you know, we discussed it's not terribly accurate. of this clock. And so yeah, divide by 16. That's fine, but we're not actually seeing divide by 32 on the rest of them, right? So why is that? I'll explain that now. Is anybody watching? Put a comment on. No, nobody's watching. Well, last video I got a few comments, but I'm trying to test that I can actually see the comments. I'm actually not sure that I'm in the right place now. Oh yeah, somebody's watching. Good, thank you. Oh, I'm adjusting the zoom and looking at the wrong window. I'm looking at the feed at what you're watching, and then that's a few seconds behind. Yeah. All right. So let's assume. Let's forget for a second that it's the first stages aren't. There's no output, but so we look at the first output, right? First output, so that would be Q4. All right, and then we're looking at Q5. So I'm looking at the scope. Hold on. Okay. So I'm looking at the scope and I'm seeing that so it's the falling edge. I'm going to mark these. So Q5, the falling edge, it goes from high, low, then it's low until 1, 2, so 1, 2, yeah, till here, right? So, sorry, 1, no, to here, right? Then it's going high. It's going again like that. And then Q6 just gonna move so I see it. Okay, Q6 this is going high until the falling edge. Oops, yeah, the whole thing. Then going like that, that. Now, I'm going to mark it so it corresponds to what we're seeing on the scope. Okay, so now we're going to look at each edge of the clock. Okay, and just get the states. So this is 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, so 1, 0, 1. Okay. So this is the least significant bit and the most significant bit. In other words, when we write in binary, we would write MSB to LSB. So let's look. Let's start here at 0, 0, 0, 0. So we have 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and then 1, 0, 1. And then it goes back to 0, 0, 0. So we have we have a cycle now here of 0 to 5, which is 6 states, which kind of corresponds to the 6 states of the die, right? So that's why we're not seeing the continuation. Somehow there's a reset here, and it cycles through once it reaches 5 or 6, and that's exactly what the circuit does. So let's look at the circuit. The circuit is supposed to give us a the 6 states of a die from 1 to 6, and it does that, but not necessarily in order. That is, it counts in order, but it doesn't give us the order from 1 to 6 that corresponds to the counting. And you can see that. Actually, can't see that very well because it's kind of sort of dark on dark on the print, but you see 0, which corresponds to 5, a roll of 5, 1 will correspond to a roll of 3. That's what I mean. So there's a mismatch there, but that was done by the clever people at Elector to minimize the circuitry, and it's very elegant once you look at it and see how efficient it is. So the problem is that if you have that count 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. So that's 0, 1, 2, 3, 4, 5. That's all you need, right? If now we went to state 6, 1, 1, 0, that would give us a state, that would give us a reading that doesn't correspond to an LED, a die state. So ideally, what we want is that in this case, the circuit resets. And that's exactly what happens here. What we need to observe when we look at this sort of state diagram is that we have these bits, so MSB, LSB, and we know that when we reach the count of 6, the seventh state, 1, 1, 0, we need to reset. And the observation is that's the only state that has a 1, 1 up to then, right? The next one would be 1, 1, 1, but that we don't care about. The only state up to then that has 1 as the MSB, and the next bit also 1, is this state. So we want to reset by creating logic that that connects this to the reset, but only on this condition will the circuit reset. So that's like an AND gate, right? So in all others, if we connect, say, call this A and B, we connect A and B here. Only when A and B are 1, this is 1. So another way of doing this, instead of putting a logic gate in there, which is possible, but it would cost a chip, right, to put in there, and normally, well, now they do, but well, you can get this SOT23 package that is an AND gate, but that would be surface mount and a bit less elegant than this, the solution that is in the circuit, where there is a diode here that, so we're looking at the reset signal here, right? This is the reset, and this reset is pulled, is always low in all the states up to then, right? This is called a wired end, and when this is low, there is a 1 volt drop here. And this still remains at low, at 0. So it's not reset. Sorry. This would be at about 1 volt. So, and it's still not reset. But once B4 and B5, this A and B, are 1, then this signal is high, is allowed to be high, and the circuit resets. So what ends up happening is that we have a very, very brief moment where the state is at 6, which is an invalid state ideally, but it's so short that it barely affects the circuit, and we will find that signal. It is incredibly short, and immediately resets to state 0, and that's why we see that's why we see this ending. Where did I have that? The cycle ending right here. And I don't think it's going to be able to pick up, but you can sometimes see an artifact. It's not an artifact, but a very, very small pulse here. And that's from the reset. So let's try to find this reset. So I'm going to turn off all the signals. Oh, no, not that one. And I'm going to go to the reset signal. Have that. Now I'm going to trigger on channel 1 again. And do you see this reset emerging? Right. So this is the reset signal, and as you can see, it's about 200 nanoseconds width, and we are at this 1 volt per division. So this diode drop that I talked about, and then it goes to say 1, 2, 3, 4, 4.5 volts. That's when the reset signal, the threshold of that reset pin for a logic high happens, and then it immediately goes back low when the chip resets, right? The counter resets. So that means that we have this extra 200 nanoseconds in the rolling, cycling through, that the state is actually an invalid state for our purposes, for the purpose of the die. It's an invalid state. So it's not on top of all the other tolerances, it's not pure. It's not an exact. The states don't have an exact time. So if you're going to Vegas with this, they'll probably kick you out. There'll be somebody who knows electronics there, and they'll tell you, look, this is not fair, and that's not a fair die. So you're not welcome at this establishment. Your money is not welcome here. So yeah, so we found that one. That's nice, no? I think so. Well, let's keep it live, keep it going. Yeah, I feel like I've done this somewhat in reverse, because we haven't gone through the actual states of this thing. But now we're ready, right? We're ready because we know what is happening here, and we can see why we're getting the states that we are getting, right? Why we're getting a 6 when the the count is at 0, 1, 0. So let's try this out, right? So we have 0, 1, 0. That's the most significant bit, so it's 0. This is 1, and this is 0. So, right. Let's look at the 1. The 1, this is a PNP transistor, which means that it will be on when the base is at 0. So that means that this is off. But we have here 1, and it's going through this branch here, and since this is 0, there will be current going through, right? So we'll go current. So we have these LEDs on, right? Now, that's okay. We're looking for 6, right? So that's good. This is off, right? So that means that this middle one isn't going to be, even though this is 0, there's just no voltage here. So that's not going to be on. Now this is connected. There are 2 branches here. There's this branch, and then this branch, and those are connected to power. So that means that if there's a 0 on here, there will be those will be on, and indeed there is a 0 here, or ground, right? So so these are also right. So we have our 6. I printed a few more. So our one viewer, do you want to choose one? Me to do? I won't do all of them. No? Alright, well, I'll take a second. Maybe he's not there anymore. No. Alright. Let's do a 1. A 1 is 0, 1, 1, which is 0, 1, 1. Okay, so let's look at this branch again. There's a 1 here. Well, that's good. Oh, but there's a 1 here. So that means it's not on. Now let's look at this branch. Okay, there's power. That's great. But there's a 1 here. That means there's nothing there either. And the same for this one, right? Nothing. Nothing. But, oh yeah. So, this is on, and this is off, but through this diode, we are going to power this LED. So we got 1, and then we have a 0 here. So there we have it. well, you could do the rest as an exercise. It's quite fun. And I think I covered all that I wanted to cover with this. Let's bring this back here. The specimen. Oops, what's going on? Okay, I don't know what happened. Why is it? Could be some shorts because of the probes. Okay. Well, like I said in the previous video, another aspect of designing with these devices is that you have to figure out how much current the output can supply. And in this case, the output supply is quite low. Drive current, oh no, that's, it was somewhere here. Blanking. Drive current at pin 9. No, that's not it. Right, there we are. So you're looking at this table here. And it's telling you at different output voltages and a different power, the power, the voltage. It's late here. It's 8:15. A bit hungry. I wanted to do this first thing in the morning. Well, anyway, yeah, a different VDD, which is the input voltage to the device, and a different output voltages. Oh, actually, what is this? V in. V output. I'm not sure. Anyway, I'm a bit out of energy. But here you see at 25 degrees, normally they're giving a bit more data at 25, and here it's from minus 55 to 125. You can see that about, in our kind of 10 voltage-ish, we're at about 1 milliamp per output. And that is quite low, right? So LEDs normally don't shine very well at 1 milliamp. But luckily, I found these Cree. Sometimes when I'm looking for a particular brightness current combination, I'll set up maybe 20 different, or 15 or 12 or 13 LEDs at a particular current, and I'll see what I'm getting so I can have the right effect that I'm looking for. And if it's a power sensitive, if it's battery powered, I want to minimize the amount of current that the device is taking. And so I had to find very efficient LEDs. At most, they could be driven at 1 milliamp. And I found these Cree LEDs. And as I say in the previous video, those, as you see them now, are running at less than, well, now you're seeing them on and off because it's cycling through, but as you see them now, they're at less than half a milliamp, 500 microamps, which is quite impressive brightness for that. And I had to keep increasing the current limiting resistor until I got it to be low enough in brightness to be acceptable. So it was kind of the opposite than normal. I'm quite happy with these Cree LEDs. They're a bit more expensive, but totally worth it. Okay. How long has it been? An hour and 11 minutes. Alright. So, let's go back to seeing me. Hi. That's it for this time. I think people have gotten the PIPS project late last week, and a lot more people are going to get them. You know, we shipped over 500 packages last Tuesday, and so everyone in many places in the world are going to start getting them, and I hope these videos are helpful. We're going to do, I aim to do more of them now that we have our setup for this sort of thing, and I'm actually enjoying it. Of course, we have to iron out the little things that happen, but that's kind of natural progress of things. If you wanted PIPS, this project, you need to be a Boldport Club member, and there's, I think, just under 40 still in stock. After that, we don't make more. So, and you can only buy them if you're a member. You buy them at the club shop. So, to get more information about this project, it's boldport.com/pips, and to become a Boldport Club member, it's boldport.club. Thank you for bearing with me, and whoever's watching it now and later, I appreciate it, and see you next time.